Okay, here is another type of game that we look at this week. So in reality, it's not always the case that we only have a few possible options or strategy which each player could choose. Rather, the decision involves a range of value for certain objects. For example, again, if I want to decide the quantity or the price of pho that I should sell in order to compete with the pizza guy next door, then that's a range of value. Because, for example, let's talk about price. Between €5 and €6, there's already 100 different values for each cent, right? So in that case, would be very complicated to apply what we have done so far. Therefore, we could apply calculus to solve for the Nash equilibria. And this makes it possible for us to analyze at which point of that range the equilibrium action will occur. For this setup, we will take the strategy of common as an example. So this is a very classical and popular example to study the game in continuum of action setup, and it's also a very popular situation that we see in real life, in which a common property is used by many different users and could easily get to overuse. For example, with environmental factors. So the story is there's two herders and they decide how many sheep to graze on a common area, grassland, for example, in the village. The problem arises when this common area is usually small, limited, and then can be easily succumb when overgrazing occurred. So what happens when they put too many sheep on this area? Resource is depleted, right? And it could at the end harm both parties because they can't graze the sheep anymore. And for that, they have to decide how many sheep to graze. So the objectives, of course, to maximize the value from grazing the sheep of each individual, given the limited resource. The first step to analyze this game is to choose a proper modeling approach for it, assuming that we have the value of grazing on this common area per sheep is given by some function of the quantity that each person decide to graze on this area. So header 1 will graze Q1 sheep, and the second one will graze Q2 sheep. And for each person, the value depends both on his or her decided quantity and also the quantity that the other decide. Now, this is the first thing. Then how to put that into a game and to solve for the equilibrium, I show you on the board. Okay, so we have players, we have their strategies or possible actions, which is like a range of values, the number of ships, right? Now we need the payoff. What is the payoff in this situation? Is a function. It's a function of some number of ships and the value. And here note that the value of grazing per ship is the same for each herder. So let's say we have payoff function. Again, the payoff, we could use the usual notation, which is U1 for herder 1, when he or she grazes Q1 and the other grazes Q2. Equals, what is the payoff? Easy. The value per ship times the quantity of ship he or she has. So Q1 times V of Q1, Q2. Note that the value per ship applies for both, and that also depends on the number of ships that each player or each herder have. Now, so this is the common strategy. Equals, just plug the value in, Q1 times 120 minus Q1 minus Q2, right? I open this bracket here. Okay. And for herder 2, it will be Q2 times V again, right? Equal Q2 times 120 minus Q1 minus Q2. And when you write down these payoff functions, you actually writing down the normal form of this game. So the normal form in this case just simply the list of all the payoff functions of each player. Now, the best response for player 1, how to define the best response. Now again, think about it as a maximization problem. As a herder, you wish to maximize the value you earn from grazing the ship, right? And this is the payoff. So you actually maximize your payoff. It's always the case in a rational setup. Now, so the problem becomes max U1, Q1, Q2 equals Q1 times 120 minus Q1 minus Q2. And we could already have the first order condition, which is derivative of U1 with respect to Q1, right? Because that's what you got to decide. Equals. Here I write down, factor out everything so it's easier. So 120 Q1 minus Q1 square minus Q1 Q2, right? So So the derivative will be 120 minus 2q1 and then minus q2, and that should be 0, right? First order condition of maximization, which we could also rearrange to solve for q1. So that means 2q1 equals, just put it to the other side, 120 minus q2, right? And that's equivalent to q1 equals 60 minus q2 divided by 2. And this, what is this? It is the batch response function of hurdle 1 as a function of q2, because now you only have q2 inside there. Remember what we did with the battle of the sexes. At the end, when you have batch response, you also have like the strategy or the action of the other inside that batch response function, right? Now for player 2, who is the herder, the other herder, is actually symmetric. Why? Because you have the same value per chip here. So the batch response for herder 2 as a function of q1 is given by q2 equals 60 minus q1 over 2. Verify yourself if that's true or not. No? Then the next question is how to solve for the Nash equilibrium given this batch response function. So the Nash equilibrium can be solved by realizing that, again back to the definition, it must be the place where both player or both herder must have jointly their batch response. So if you look at this batch response function, it's actually a linear function. So q2 is a linear function of q1. On the other way, q1 is a linear function of q2. So if you put these two functions on a graph, they must intersect. And any quantities at the equilibrium must satisfy this batch response coming from the first order condition of the maximization problems. So we could do that first numerically or analytically by, let's say this is 2 and this is 1. Substitute the second equation into the first equation. What will we have? We will have the first equation is q1 equal 60 minus q2 divided by 2. I will write 1/2 here first, and then q2 is the whole term over here. Substitute it in 60 minus q1 divided by 2, right? And we write again q1 equals 60, now simplify everything, minus 60 times 1/2 is 30, right? And then minus minus again, so plus 1/2 times Q1 over 2, that is 1/4, right? Q1. And we could put everything with Q1 to one side in order to solve for it. So Q1, here on the right hand side you have 1/4 Q1. When you put it to the left hand side you have minus 1/4. And 1 minus 1/4, which is 3/4, right? So 3/4 Q1 equals 60 minus 30, so 30 left. And at the end we have Q1 start equal 30 times 4 over 3, which is 40. And this is the quantity or the number of sheep that the first herder would graze at natural equilibrium. Okay, then you plug in to the second equation to solve for Q2 start. I mean, with the symmetric property, probably some of you know what happens already, but you have to pretend as you don't know. So Q2 start equal here 60 minus Q1 start 40 over 2 equal also 40, right? So these are the solution at the Nash equilibrium of the game. Next, I will show you on the graph how the best response function looks like and where they cross. So we now draw the lines for these two best response functions on the same graph with two axes. The horizontal one is for Q1 and the vertical is for Q2. So the first one, you could, my favorite way to draw a line is to find 2 points belong to that line and then connect everything together. So I would have, for example, set, this should be Q1 and this should equal Q2 now. So now if I set Q2 equals 0, then Q1 will be 60, right? And I put 1 point on the graph already. So Q1 equals 60, right here. Okay. And if Q1 equals 0, then Q2 will be what? Because it's equal Q1 and then here Q1 is 0, so that will be 60 times 2, which is 120, right? And Q2 equals 120, so it's right here, this point on the vertical axis. So by connecting these 2 points, I get the best response of the herder one as a function of Q2. And here for the second herder, I do the same. But first I set Q1 equals 0, then Q2 would be 60 also, right? And then I set Q2 equals 0, then Q1 would be 60 times 2 equal 120. So the same thing, but let's now change the color. Okay, so the first point is Q1 0, Q2 60. Q1 is 0, Q2 is 60. So this is the first point. The second point, Q1 is 120 and Q2 is 0, right? So it's here. And then I could connect this. This is not so easy actually. Let's hope I make it. Kind of. Okay. Now, and they will cross. Where will they cross? They will cross where the point of their optimum ship, number of ship, and here's also will be 40. So this is the best response of hurdle 2 with respect to Q1. Now, and there is this point where the two best response lines intersect is the Nash equilibrium that we have just solved before. Now one last thing to realize with this game is that the quantity at the Nash equilibrium is not necessarily the best for each of the hurdle. To see that, let's first calculate the payoff. Now, so we have U1 with this Nash equilibrium quantity. U1 will be 120 minus 40 minus another 40 and times 40, right? Which would be 1,600. Similarly, U2 will be actually the same because the game is symmetric. Okay, but please calculate that when you want to verify it. Now, if Q1 start equal Q2 start equals, for example, 30 ship, what happens? Then U1 will be equal to U2, similar because now we have the same quantity, equal 120 minus 30, right? Minus another 30 and times 30, which will be 1,800, and it's larger than this. So you see, actually, when they both raise less ship, then their payoff or the value that they get will actually be higher now. So one could start from this and think about, okay, what if we maximize not their payoff separately but jointly together, like the total number of ships raised on this common area. So we could do that by setting up another maximization problem, which is max U equal U1 plus U2 equals Q1 plus Q2 times the value per ship stay the same as before, which is 120 minus Q1 minus Q2. And you maximize that joint payoff with respect to Q1 and Q2. Okay? Then we set up the first order condition. The first one is the derivative of u with respect to q1 would be, now instead of factoring out everything or distribute everything, I will just use product rule. Do you still remember what product rule? So the derivative of a product which is given by the derivative of the first term, q1 plus q2, with respect to q1, so that's 1, right? Times the second term. Rewrite. Plus the derivative of the second term times the first term. So rewrite the first term first, q1 plus q2. Derivative of the second term with respect to q1 is minus 1, right? Simple. And equal 0. Then we could simplify everything now. 120 stay the same. Minus q1 minus another q1 minus 2q1, right? And then here minus q2 minus another q2, then minus, sorry, I should not have this part here because it's confusing, q1 minus 2q2 equals 0. Okay? Then we solve for q1. 2q1, put it on the right hand side, equals 120 minus 2q2. Simplify further, we have q1 equals 60 minus q2, right? So this, let's call it the first equation. The second one. With respect to q2, actually do the same. Equals 0. That means 120 minus 2q1 minus 2q2 equals 0. Well, let's call it, don't call it 1 but 2. And here's 1. And then this is the third one. Okay. Now, what if we plug the second equation into the third equation? Substitute. That's how we usually do with maximization problem, right? Substitute second into third. Then you would have 120 minus 2q1, sorry, 2q2, because we have to substitute q1 now, minus 2 times 60 minus q2, right, equals 0. And that means, let's simplify. 120 minus 2 times 60 is 120, that's gone. And then 2 minus 2q2 plus, because minus times minus is plus, like plus 2q2, which is 0. So on the left hand side you have 0. On the right hand side you also have 0. Unsolvable. Right? Why? I mean, if you have realized earlier, these two equations, the first one and the third one's actually identical. Nothing different there. So you have two equations, right? But you only Sorry, you have two variables. But your system now down to only one equation. That's under-identified. Now, however, from the second equation here, what we could think about is we write it Q1 plus Q2 equals 60. So you know that as long as the total number of ships is 60, then the joint payoff will be maximized. That's what's set by this first order condition. But it's impossible to determine further how many ships each herder should have within this 60 ships. Okay? So the example that I give you before, for example here, when you said both 30, then they together will have 60, which is exactly this number, and it turned out that this is the maximized joint payoff. So something to reflect with the public goods are like the common resource. Now, it's hard. It's not possible so far in this setup to define how much each user should take or should make use of in order to maximize the joint payoff. Maybe it's your turn to think about that, and with a lot of environmental problems that we have right now, come up with a solution how to solve this puzzle.